Chapter 10 Aerodynamic Analysis with Structure Flexibility Effects. FAA requires the new type aircraft loads be obtained by wind tunnel testing. Wind tunnel data is usually measured on the rigid wind tunnel model, and ZONAIR can flexibilize the measured rigid aerodynamic forces by a static aeroelastic analysis. So ZONAIR solves the following equation to include the structure flexibility effect in the total aerodynamic forces, where K is a stiffness matrix provided by the finite element solver, and AIC is the AIC matrix computed by ZONAIR, and G is the spline matrix, and FR is the ZONAIR computed rigid aerodynamic forces or wind tunnel measured or CV compute aerodynamic forces on the rigid aircraft, and M is the mass matrix computed by the finite element solver, and U is the aircraft rigid body acceleration. Okay, we assume the X is a structural deformation can be superimposed by the elastic natural modes phi sub e and the modal coordinate q sub e, and we exclude the rigid body mode from the modes because the rigid body modes cannot produce internal load. So if we substitute X into here and pre-multiply this equation by the phi sub e transpose, and we can reduce this equation to this equation, where KEE is a generalized stiffness matrix of elastic mode. QEE is AIC pre and post multiplied by the spline matrix, then pre and post multiplied by the modal matrix of elastic mode. And this term becomes 0 because phi sub e and phi sub r is orthogonal. So U can be expressed by the rigid body mode times U R is the 6 degrees of freedom rigid body acceleration at CG. So we substitute U here, and when we multiply this matrix by phi sub e transpose, so phi sub e transpose times M times phi sub R is 0 because they are orthogonal. Then from this equation, if we invert this matrix, we can solve for Q sub E. Then we substitute Q sub E into this equation, and we can compute the total flexible aerodynamic forces. And this is the forces on the rigid aircraft, and this is the forces due to the incremental static aeroelastic forces, and this is the initial force. And we can in this equation, this rigid forces can be replaced by the wind tunnel measured or CFD compute forces. However, this AIC is still computed by ZONAIR. So the AIC matrix is not accurate at a transonic Mach number because it is solved by ZONAIR by solving the linear potential equation. So the AIC matrix can be corrected using the wind tunnel measure or CFD computed pressure distribution or component loads. We have two AIC correction methods in ZONAIR. One is called force correction method using the WT1AJJbook.com. Another one is downwash weighting matrix method using WT2AJJbook.com. The corrected AIC matrix can be output by the output for data and import back using the assign matrix executive control command. So the car to perform the static aeroelastic analysis is called FlexLD, and the FlexLD is referred to by a FlexLD case control command. So in the case control section, you have to specify flex LD equals an integer. This integer refers to the ID of flex LD. Flex LD further refer to the aerogen car, and in the aerogen car will calculate two set of result. The first set of result is the aerodynamic pressure on the rigid aircraft. Another set of result is to generate so-called AJJ, DJK, and FJK matrix to compute the derivatives. Okay. At this moment, you can use the IMP-CFD1 to import the CFD compute CP at the same flight condition of the aerogen car. Therefore, you replace this guy computed by ZONAIR by CFD, and all you can using CP splines or CP spline L to interpolate the wind tunnel measure CP to the ZONAIR model. Okay, and so you first you can replace ZONAIR compute CP on rigid aircraft by CFD or wind tunnel. It should be noted that because the ZONAIR panel model is a high fidelity model, so it shares the same surface definition of the CFD surface mesh. So when usually the CFD surface mesh is much denser than the ZONAIR panel model. So this replacement is very straightforward. ZONAIR just go into the CFD surface grid to find for a given panel. If find the closest CFD grid, then use that CP to replace the CP on that panel. Okay. If you use a CP spline and CP spline L, and then you have to do some interpolation. Okay, to perform static area elastic analysis, you have to specify solution 1 in the executive control command. Then you have to use assign FEM to import the model data computed by finite element solver, and you have to specify the spline input cost to interpolate the motion from the structure grid to the aerodynamic panels. And you can replace ZONAIR compute rigid aerodynamic forces by CFD or wind tunnel data using those cars. And then we have a WT1, WT2 AGH car, and can be used to correct the Aic matrix. So in other words, we use CFD or wind tunnel measured CP on the rigid aircraft to replace ZONAIR compute CP. Then we can further using WT1 AJJ or WT2 AJJ both cars to correct the Aic matrix here. So the flex LD car is referred to by the flex LD case control command. So in the case control section, you have to specify flex LD equals an integer. That integer is the ID of the flex LD both car. Then you refer to an aerogen car. In this aerogen car, you specify the flight condition in terms of angle attack, side slip angle, and the control surface deflection, and so on. And then you have to specify a dynamic pressure. The unit of the dynamic pressure must be consistent with the unit specified in Aero car. And if you want to include the follower force effect, you can put a negative sign in front of this dynamic pressure. And form, you can choose one of them to output the deformed aerodynamic model and the pressure coefficient, and according to what kind of graphic software you have. Also, you can use output 4 to output the flexibilized aerodynamic pressure coefficients on the panel model, and it's in the output 4 format. And because whenever you activate flex LD, and which refers to Aerogen car, the Aerogen car will automatically generate so-called AIC matrix. Okay, this AIC matrix actually consists of 3 matrices. We call it AJJ, FJK, and DJK. So this 3 matrices can compute the derivative of the aerodynamic pressure with respect to a displacement vector. Okay, for example, if you give a rigid body pitch mode here, and you multiply by those matrices, you will give you the dCp by d alpha. Okay, so therefore, the AJJ, FJK, DJK matrix, unlike the AIC matrix generated by the Mach car, the AJJ matrix computed by the Aerogen car, and because Aerogen car, in Aerogen car you have to specify a flight condition in terms of alpha, beta, and the control surface deflection, and so on. And those AJJ, FJK, DJK matrices depends on the flight condition. So every Aerogen car, it will give you a set of AJJ, FJK, and DJK. And to generate those matrices could be computationally costly. Therefore, you can use AJJ save to save those matrices. And later on, if you want to reuse those matrices, you can put a quire here. And as we mentioned, to perform the static aeroelastic analysis, this AIC matrix, namely the AJJ, FJK, DJK matrix, are computed by ZONAIR by solving the linear potential equation, which may not be accurate. So we have the Aic correction method. The first one is called WT1 AJJ, and it can correct Aic matrix by a force correction method, so that the force and moment computed by the correct Aic matrix match a given set of a component for force and the moment. And so the WT1 AJJ matrix generate a WT1 matrix. This is called correction matrix. And when you multiply WT1 AJJ to the AJJ matrix, and this AJJ matrix we call AJJ star, we call it corrected AIC, and then for given displacement vector, you compute the CP. This CP we call corrected CP. Then when we integrate the CP to with a component load integration vector, it will match with the given component loads. Okay, and the method of doing that is we use the Lagrange multiplier method, where the difference between the correct CP and uncorrect CP, CP is computed using this equation with the WT1 matrix, and this will become the objective function, and the f given is the constraint function. So we use the Lagrange multiplier method to generate the WT1 matrix. Okay, so the car called WT1 AJJ, and if this ID match with the Aerogen car, and then the AJJ matrix generated by the Aerogen car will be corrected using the force and moment correction method. If you have a half-span model, and you could have a symmetric AIC and anti-symmetric AIC. If you have a full-span model, then you only have an asymmetric AIC. WT1 file it refers to a file name where you store the WT1 matrix. And after that, it's open-ended protocol, and this one is referred to a set of WT1 FRC matrix. Each one will give you a constraint function. Okay, so it allows you to specify multiple component loads as a constraint functions. And so the WT1 FRC actually because we want to compute generate the WT1 matrix times AJJ, if we give a displacement vector and integrate the resulting CP by a loads integration matrix, that will give us a component loads. Actually, this component loads is the slope of the component loads. So you give two sets of component loads, and then the A1, A2 is at a different condition. Say, if you measure if you measure the wing loop bending or the hinge moment of a control surface at angle type 1 degree and 0 degree, and you say, okay, this is the hinge moment at 1 degree, this is the hinge moment at 2 degrees, and then the A1 should be negative 180 divided by pi in order to convert the degrees to radian. Okay, let's look at what this curve look like. Okay, this one is referred to by the WT1 AJJ, and type specify a displacement vector. Okay, so this displacement vector, it could be a structural finite element mode, or control surface kinematic mode, or a low marker, a low mode, or a rigid body mode. And label, if the type equal to FEM, label is integer and it represents the index of structural finite modes. If it's A sub z, and label is label entry of the A sub z or AES link to define the control surface. If it is low mark, label is integer and represent the ID of the low mark car. If it's rigid, then if in the WT1 AJJ, if it's a sun or a sun, then you have three choices. You have 4.5 mode, plunge mode, and pitch mode. If you have anti, you have a Y translation, yaw mode, and roll mode. If you have full span model, you can choose one of them. And after that, you specify, you refer to a low marker. For example, this low marker represents a wing loop bending moment. Then you give a dynamic pressure where your measure the wing loop bending moment at, say, angle tag equals 1 degree, and another wing loop bending moment at angle tag 0 degree. So you will use this equation to compute the slope of this wing loop bending moment with respect to angle tag. Okay, for in this case, I choose type equal to rigid, and then I choose the label equal to pitch. So I have a pitch. Because pitch mode is kind of an angle tag. I have two the wing loop bending moment at two different angle tags, and then at a given dynamic pressure in the wind tunnel, and I can use wind tunnel data to calculate the derivative of the wing loop bending moment. And likewise, I can do the same thing for shear with wind loop shear. Okay, and those will give me the a constraint function. And however, we found out to construct the WT1 FRC matrix and the WT1 AJJ is very time consuming. Now, if you have a CFD compute CP on the rigid aircraft, we have a car called WT1 CFD. The WT1 CFD can internally generate the WT1 AJJ and WT1 FRC matrix to make your life much easier. Okay. So the first one, to activate WT1 CFD, in the case control section, you must have the WT1 CFD case control card. And then this refers to Aerogen card. The Aerogen card, okay, defines a flight condition. For example, in this case, you define angle attack equal to 1 degrees. Meanwhile, if you have CFD solution at angle attack 1 degrees, you can use the IMP CFD or IMP CFD1 to import to replace the ZONAIR computer CP at angle attack 1 degrees by those CFD computer CP at 1 degree. In other words, in this equation, we replace the ZONAIR at 1 degree by the CFD computer CP at 1 degree. Okay, the next one, we have a IFAJJ. We can store the corrected AJJ matrix, and we can store corrected FJK matrix. We can store corrected DJK matrix. Also, we can store the WT1 matrix. Then after that, the trim bar, it can be either alpha or beta, or the entry label listed in the Aerogen card. So why would we want to do that? Because we want to compute the slope, the derivative of the load. Okay, and then delta is the perturbed value in degrees from the flight conditions specified by the Aerogen card. For example, in the Aerogen card, I specify the angle attack equal to 1 degree. Then I have a CFD compute CP at 1 degree, and also I have another set of CP computed by CFD at 2 degrees. So I can say, okay, I have incremental perturbed value. So I put a 1 degree here, and then I say trim y equal to alpha, and then the IMP CFD is the CFD computer CP at 2 degrees. So you use the IMP CFD and CFD1 card, and those cards at 2 degrees. Okay, and the low mark card here is I refer to a set 1 card. In set 1 card, we list a set of identification of the low mark card. So in other words, I wanna, for example, the first low mark card defines wind rule bending. The second one defines wind rule shear. So those become the constraint function. And I have CP CFD and CP AJJ. The first one is filed to store the derivative of the pressure distribution by the CFD. So because I have a CFD computed at 1 degree, CFD computed at 2 degrees, I use a finite difference to calculate the derivative of the CP computed by CFD. And this one I store also the derivative of the CP, however, computed by the corrected AIC. Okay, this card will internally generate WT1 AJJ and a set of WT1 FRC. Then process the WT1 AJJ to generate the correct AJJ matrix. The WT1 CFD can only be applied to a full span model. Okay, in other words, the entry XZ sin in LZ card must be known. So the internally generated WT1 AJJ and the WT1 FRC is shown here. For example, if I have a first, if I have a pitch mode generate 3 sets of component load. For example, this is when you bending moment, when you shear, when you torque, and also I have a horizontal tail deflection angle. So this probably is horizontal tail bending moment and shear and torque and so on. So I have a 1, 2. So I can process. ZONAIR can process this internally generated WT1 AGG car. And for trim y equal to alpha, the angle tag is perturbed as alpha plus alpha naught and plus delta. Alpha naught is angle tag specified in the Aic car. And if it's beta naught plus delta, and beta naught is the side slip angle defined in the Aic car. If the delta naught is the control surface deflection angle defined in the Aic car. And so delta is the perturbed one. Say I perturb, if the Aic is 1 degree, and I have a delta equal to 1 degree, so I have 2 degree angle tag, and those CFD compute CP at 2 degree angle tag is import using this entry. So this low mark car, also you will those low mark car define a set of component force and moment. The derivative of those component force and moment with respect to the mode vector W are computed by the following equation, which is given here. And F given is the constraint function. L is the low integration matrix. We assume the dynamic pressure to be 1. Okay, the second Aic correction method is called WT2 AGG. And we use this one. We use the downwash weighting matrix method. The downwash weighting matrix is computed WT2. So AGG times WT2 will match with a given CP. Okay. Again, this one refers to Aic car. And soon you have a half span model, you have a symmetric, anti-symmetric Aic matrix. Yeah, if you have full span model, you only have an asymmetric Aic matrix. And this one defines a displacement vector. And you have thin, A sub Z, low mark, and rigid. Just like that WT1 AGG, this one defines a displacement vector. And the WT2 file allows you to output the WT2 matrix, and then you have form it to so your in you have two choices. One is DMI, one is CFD. DMI you use the DMI card to import the CFD. If you see a CFD, you use the IMP CFD1 or IMP CFD to import the CFD. So you import 2 sets of CFD solution at a different angle tag, and then you can calculate the DCP by the alpha. Say if you say type equal to rigid, and the label equal to pitch. So that you define a rigid body pitch mode, and then you use 2 sets of CFD to compute the derivative of the CP, and then you generate the WT2, the downwash correction method generate a WT2 matrix. So AGG times WT2 times a given say pitch mode will give you the derivative of the CP, which match with the CFD computer derivative of the CP. So this slide shows the influence of a static area elastic effect on lift coefficient, and the black one is the rigid one, and then at different altitude, if you include the static area elastic effect, you can see the CR is lower than the rigid. This is for a transport type of aircraft, because the transport wing is a swept back wing, and under the static aeroelastic effect, the wing will deform to have the wing tip has a pitch out, wash out effect. So the local angle attack at the wing tip will be lower. Therefore, you have lower lift. And output 4, you can use output 4 to output the AJJ, DJK, FJK matrices. The name of those matrices are listed here. And also, if you design a transport aircraft, and then the aerodynamic people design a so-called desired the best aerodynamic shape. So under they call cruise shape. Under this cruise shape, it will give you the best L over D. However, because the static aeroelastic effect, the wing will deform deform from the desired shape. So then you don't have a desired shape during the cruise. One way to circumvent this issue is to design a jig shape, and that at the cruise condition deform back to the desired shape. This jig shape can be determined by ZONAIR. So this the formulation, how ZONAIR calculate the jig shape from the cruise shape. And so you can see we can plot the blue one is the desired shape, and the red one is a jig shape. So under the cruise condition, the wing will deform from the red jig shape to the cruise shape, and so cruise shape is the desired shape, which gives us the best L over D. So for the swept back wing, the lift coefficient of the jig shape is higher than the cruise shape, because for the swept back wing under cruise condition, the wing twists downward due to the aeroelastic effect. In other words, it has a wash out effect. It twists down. The wing tip twists downward. Therefore, to ensure the jig shape under cruise condition can deform back to the cruise shape, the jig shape must have a built-in twist-up wing. Okay, so this twist-up wing of jig shape generates a higher lift than the cruise shape. So you can see, the jig shape is shown by the blue one. The cruise shape is by the red one. So the lift generated by the jig shape is higher than the cruise shape. Therefore, without the CP correction from cruise shape to jig shape, the predicted load should be underestimated, become non-conservative. So to define to determine the jig shape, this one is activated by a jig shape case control command. You give a dynamic pressure, you give the aerogen car, which define the cruise condition, and also on the rigid aircraft and on the cruise ship. And so, meanwhile, you can replace ZONAIR compute CP on the cruise ship by the CFD or by internal measure using IMP CFD or IMP CFD1 and the CP spline car and so on. And as far as CP, you can output the pressure coefficient on the jig shape stored in the output form. And then if you want to plot it, you can plot it using the what kind of graphic software you have, and you can scale up the difference between the cruise ship and the jig shape for the clarity of the graphic display. And also you can refer to the panelist 2, panelist 3 car and those panels in those cars are whose shape will be excluded from this jig shape analysis. And know that when you in the output file, when you compute the jig shape, you output the generalized coordinates due to the deformation from the cruise ship to the jig shape to the cruise ship. Okay, now if we want to calculate the CP on the jig shape, okay, you use the jig CP case control card to refer to the jig CP, and the matrix name contains the generalized coordinate computed by the jig shape module. So you can cut and paste this DMI card from the output file when you perform the jig shape analysis. Paste in the input file when you want to do the jig CP analysis. Again, it refers to the error gen card, and you can use IMP CFD and CFD1 CP spline card to replace the linear computer one, and then you have file. You can store the corrected pressure in an output format, and then also you can plot the CP on the jig shape. Okay, that's the end of chapter 10.